Okay, I will just slowly already start with the introduction of this talk. So again, hi everyone, welcome back after our break. I hope that you've also had some kind of break the past few weeks, or have at least been enjoying the summer or winter, whatever season it is where you are right now. At least at PaleoPerks we had a break, so now we're back from our hiatus in July. And we are starting this season with a talk by Adam Woodhouse from the Open University in the UK, who is going to talk about macroevolutionary volatility and upheaval that governed the Cenozoic marine realm. So the format of today's seminar, if you're new here or if you haven't been here, which includes me now as well, I start with some welcome and announcements. I'm doing that right now. My name is Nina, by the way. Then we have Adam's talk for around 30 minutes, followed by a moderated Q&A of around 10 minutes. So during the talk, you can already send your questions either in the chat or to the questions at PaleoPerks host, which today is Salman, if you want to ask them anonymously. And then Adam also has agreed to stay for tea time. So if you just want to have an informal chat with Adam, then feel free to stay after the talk. A bit more housekeeping before we start. So PaleoPerks values the participation of all folks interested in the paleosciences. Please remember to abide by a code of conduct during today's seminar. Also, please keep yourself muted during the seminar, just out of respect for our speaker. And like I said, you can ask questions by chatting to the questions at PaleoPerks host Salman, if you want to stay anonymous, or send them directly in the chat if you want to be mentioned by name, or if you want to ask them, just use the raise hand function and we will unmute you. If you have any technical issues, also please send a message to Salman. We have closed captions built into Zoom, so you can use the CC button to show or hide them. They are set to English automatically. And then last but not least, PaleoPerks only works because we have so many early career researchers that are doing very cool and interesting work and that are willing to give a talk. So if you either have a colleague who could give a talk, or if you want to give a talk yourself, then please nominate them here. This link will be dropped in the chat. You can also nominate yourself. You're very welcome to do that. And then finally, we also would really appreciate it if you can fill out a weekly feedback form. This is just for some anonymous information for demographic reasons, so we can see who shows up and maybe who doesn't show up, just so we can continue to improve. So that will also be dropped in the chat. So that's enough about PaleoPerks, and a bit more about the speaker, Adam Woodhouse. Adam, this is not a complete CV of him, but he did his master's in applied and petroleum micropaleontology at the University of Birmingham in the UK, followed by a PhD in macropaleontology at the University of Leeds, also in the UK. He did several postdocs, including one as a fellow at the University of Texas in the US and a lecturer position at Cardiff University in the UK. And recently, he has been appointed as a lecturer at the Open University in the UK. Apart from that, he is also the secretary of the Micropaleontological Society at the moment. So with that, Adam, I would like to thank you again for giving a talk today, and I invite you to share your slides and start your presentation.
Okie dokie. Can you see my slides?
Yes, give me 1 second for it to load. Yeah, looks great.
Sure, cool. Great. Okay. Well, thank you for that fantastic introduction, Nina. I'm happy to be presenting today. So I'm Adam Woodhouse. I'm a lecturer at the Open University. And today I'm going to talk to you about some of the work myself and my colleagues have been doing looking at the Cenozoic marine record. In particular, most of my research focuses on marine microfossils and using them as a proxy to understand the Earth system, but also understand how the kind of biological system and the Earth system respond to one another through mostly Cenozoic geological time. So a quick outline of how this talk is going to, what it's going to look like. So first of all, I just give an introduction to the planktonic foraminifera and why they're my microfossil of choice and why I think they have such good utility for understanding some of these questions. Then I'll just give a quick introduction to the Cenozoic and the key events in the Cenozoic, which there are many, but the key events which are useful and relevant to this talk. And then finally, I'll be then looking at some of the research some of my colleagues have been and myself have been looking into. So first looking at compositional variability in time and space, which is led by my colleague Micah Morrison at the Santa Fe Institute, and then work that I've been doing for the last 3 years or so, which is how long it's taken to write this paper, looking at the response of the kind of the biological pump and the potential twilight zone of the ocean to the inception of ice sheets on Antarctica at the Eocene-Oligocene boundary 34 million years ago. So first of all, why the planktonic foraminifera? They are single-celled marine protists with calcium carbonate shells, which are called tests. So single-celled organisms, they are drifting around in the upper ocean as plankton, and when they die, they sink down as marine snow and settle to the sea floor. This is the sea floor, which is absolutely beautiful, and if we grab a piece of the sea floor and put it under the microscope, we can see all of these amazing little microfossils, which can tell us lots about different aspects of our Earth system based on their geochemistry and just their assemblages and abundances. So down on the seafloor, if you're in a very productive area for planktonic foraminifera, it can be up to 100,000 individual skeletons per gram of sediment, which is very, very abundant, very, very useful for looking at populations. Because they're so abundant, because they're made of calcium carbonate, they fossilize exceptionally well, and they have a more or less continuous record since their evolution in the Jurassic. And then because of this well-preserved record, they have a highly refined taxonomy. So for the Cenozoic in particular, they have the best species level record known to science, which means that we can look at their different morphospecies and assess the ancestor-descendant relationships and look at the intergradation between different species through geological time, looking at the timing and the rates of these kind of evolutionary events between different morphospecies. And because they're well preserved, and the reason why we know so much about their phylogeny in particular is through a combination of industrial plus scientific ocean drilling. So in particular, scientific ocean drilling has been going since 1968 through the Glomar Challenger and the JOIDES Resolution, these amazing scientific ocean drilling vessels. And because people have been meticulous about recording the occurrences of planktic forams within the fossil record, while we've been drilling these 400 kilometers or so of core, myself and my colleague, Dr. Isabel Fenton, joined forces and created the Triton dataset. So we went to all of these different occurrence records since 1968, collated all of that data into a single holistic dataset and created Triton, which has over 500,000 individual presence absence records, but if you add in the quantitative data that we have for forams, it's about 9 million individual potential fossil occurrences, so making it the largest fossil occurrence data set that we currently have at hand. And if we just plot, let's say, a spatio-temporal plot through the Cenozoic, so this plot here on the right is time along the bottom from 66 to 0 million years ago, and the latitude of where these occurrences are. We can see that Triton has a really global record going back through most of the Cenozoic, but with clear gaps in the polar and tropical regions for especially the early part of the Cenozoic. Another key factor is that those calcitic skeletons preserve the entire life history and ontogeny of our organisms, and the different kind of shapes and sizes and morphological characters. Many of them do have morphological significance and also functional significance. So one of the key things that my PhD supervisor did was take all of the Cenozoic planktonic foraminifera and assign a morpho group specification, assigning them to 19 distinct potentially functional morphological groups. So another way of kind of looking at disparity. But then also those calcareous skeletons also have some interesting geochemistry where the calcium carbonate, the carbonate side of that preserves different aspects of ocean chemistry. So if we take some of these individual skeletons and put them into a mass spectrometer, assess the oxygen isotopes on the y-axis and the carbon isotopes on the x-axis, it can tell us generally where they live in the water column. So an increasing ratio of carbon-13 is a sign of an increasing photosymbiont presence or activity. So usually higher delta-13C in the upper part of the water column in the photic zone. Whereas if we combine that with our oxygen, a higher ratio of oxygen 18 means they were calcifying in colder waters, generally speaking. So combining these two isotope systems together gives us an idea of their ecology. And again, my PhD supervisor, Tracy Ayes, during her PhD, assigned all of our Cenozoic species to 6 distinct ecological groups. Those living in the surface mixed layer, the SML, with and without photosymbiotic algae in association. A bit deeper down in cooler waters, there we have thermocline dwellers, and then even deeper we have subthermocline dwellers. And then there's 2 distinct groups based primarily on their biogeography, living in the high latitudes and high productivity and upwelling areas. But ultimately, what this means is that the fact that we can assign all of the entire phylogeny to these morphological and ecological groups is really useful for understanding macroevolutionary change, because where morphospecies and species in general kind of wax and wane through time, they evolve, they become extinct. These evolutionary ephemeral, these functional groups are consistent through the entire phylogeny, through the entirety of the Cenozoic. So we can look at how different aspects of the water column, how different morphologies are interacting with Earth system change. Okay, so hopefully I've convinced you why I believe that planktonic foraminifera are really useful for addressing topics such as the title to this talk. But now let's look into the Cenozoic and what events are relevant towards the rest of this talk. So the Cenozoic is a highly dynamic Earth system, as are pretty much any of the time periods that we're interested in as geologists, and even now. This plot in particular is a fantastic plot by Thomas Westerhold et al. From 2020. And this is basically summarizing the temperature evolution of the Cenozoic. So again, we have time along the x-axis from 66 to 0. And on our y-axis, on this occasion, we have the average global surface temperatures compared to the modern day, generally speaking. So the black line is our surface temperatures. And what we see in general from this plot is that the first half of the Cenozoic is this kind of hot and warm house world. This non-glaciated world, I put non because there were glaciers and there have been through pretty much all of the Cenozoic, but there weren't extensive continental ice sheets. And then the second half, we have this kind of glaciated world where the Antarctic ice sheet forms permanently across the Eocene and Oligocene boundary on Antarctica. So generally speaking, it's kind of this hot and warm versus this cold and icy, split by about 33, 32 million years. Going through the Cenozoic, the important events for this is we start the Cenozoic with quite a bang with the Cretaceous Paleogene mass extinction event here at 66 million years ago. So an asteroid tumbles out of the asteroid belt and collides with the Yucatan Peninsula and what is now modern day Mexico. The key victims, other than the non-avian dinosaurs on land, in the oceans, we have marine reptiles, ammonites, question mark, because there's some evidence they may have survived for 10,000 years or so in certain localities, especially on the Gulf Coast. But in particular, the planktonic foraminifera are really hardly hit. The worst extinction for the entirety of their fossil record, of about 90% extinction rate at the KPG mass extinction. So moving on from the KPG, a pretty important event, but we don't go into detail here, is the Paleocene-Eocene thermal maximum 56 million years ago. Here we have about a 10-degree, it's the most geologically rapid natural warming event through the entirety of the last 66 million years, with about 10 degrees rise in temperatures over the course of tens to 100,000 years or so, and then it kind of drops back down and we get a recovery of the Earth system. Then we get a general warming in towards this hothouse world of the early Eocene from about 53 to 49 million years ago, just kind of a general interval of sustained warmth globally. And then from about 50 million years onwards, we have what's known as the descent into the ice house, where the Earth system has generally cooled down over the last 50 million years. There's a few hiccups with some thermal maxima here and there, but generally speaking, we have this cooling trend. The the coolest. One of the most rapid cooling events is the Eocene-Oligocene transition, which I'll go into more detail in the last part of this talk. But here we have inception of the Antarctic ice sheet. So here, due to tectonic changes, the opening of the Tasman Seaway and the opening of the Drake Passage, as well as recent evidence, a paper came out in the last few weeks showing mountain building events allowing for ice sheets to form easier on Antarctica around this time. We kind of have this thermal isolation, establishment of a kind of proto-Antarctic circumpolar current, thermal isolation of Antarctica, CO2 drawdown by a number of different factors, and ultimately we get ice sheets forming on the Antarctic mainland. And here we have the most extreme extinction rates for our planktonic foraminifera since the KPG at about 20% across the Eocene-Oligocene transition. The next event, which is potentially of interest, and this is a kind of recently formalized, not really formalized, me and my colleagues are calling it the early Miocene event for the time being before we figure out exactly what it is. But about 19 million years ago, there's nothing going on when it comes to temperature. But interestingly, in biological systems, myself and my colleagues have discovered that from the base of food webs, be that from proxies from bacteria through to diatoms, radiolarians, forams moving up food webs, all the way up to cetaceans, there is these interesting ecosystem changes centered around 19 million years ago, and possibly associated with some opening and closing of some ocean gateways. And a very, very shameless plug that myself and my colleagues at the Early Miocene Working Group have a IDP Spark proposal funded to assess what is going on during this interval, where we will be ideally in the next week or two finalizing the research team of scientists who will then descend upon the Bremen core repository to sample some cores and see if we can work out what is going on around this event. But yeah, important potentially to a later part of this talk. And then we move on to this mid to late Miocene cooling around this time. So after this interval here, known as the Miocene climatic optimum, we then have a kind of exacerbated cooling following that. And this is a really important time for our forams in particular. Initial work with the Triton dataset led by Isabel Fenton showed that around 15 million years ago, during this time interval, we have the origination of our modern style biodiversity gradient. And then following that work led by myself and Dr. Anshuman Swain, we looked at the last 15 million years of the Cenozoic here along the bottom, it's 15 million years, and used bipartite networks, a method to basically look at community structure, and basically based on these eco groups that that I mentioned earlier, looks at kind of eco group community structure, where this metric we've applied, this eco group specialization index, represents in red areas where our eco groups have these kind of generalized communities, and these blue areas where they're very specialized communities. And what we noticed was there's this kind of equatorward migration of generalized communities over the last 8 to 10 million years, which we assume is due to this mid to late Miocene cooling, which operated by allowing more oxygen and particulate organic carbon deeper into the ocean, which kind of allowed for this radiation of organisms down into the twilight zone. So relevant to the later part of the talk, this is when the true oceanic twilight zone appears to have started to form based on this cooling, this late Miocene cooling event, whereas later on I'll be talking about this Eocene-Oligocene cooling event and potential relevance. So yeah, this work with networks has been co-led by Dr. Anshuman Swain, pictured here. The final kind of key event of the Cenozoic that is relevant to this work is the intensification of the bipolar cryosphere. So around 3 million years ago, the Greenland ice sheet really starts to form properly, and then we switch from this unipolar world from 34 million years ago to a bipolar world with ice sheets on both poles around 3 million years ago, which had all kinds of ramifications for the global structure of vertical and latitudinal temperature gradients, but also the latitudinal biodiversity gradient and where organisms are located all around the globe due to this kind of cooling and drying out of certain parts of the planet. Okay, so there we have the planktic forams, and the Cenozoic and some of the key events that I'll be talking about for the next part of the talk. So the next bit, I will be introducing this section on compositional variability, which has been led by Dr. Micah Morrison at the Santa Fe Institute. So I'll try to do justice to her work pictured there at a workshop the three of us led at a conference a couple months ago. So compositional variability. So the way we can think about this compositional variability compared to something like diversity, there's two kind of ways of looking at variation. So diversity quantifies the variability in one sample at a time. So here we have kind of three example assemblages, let's say. So these could be different time bins, these could be different regions around the globe, these could be from samples from individual sediment cores, from samples just from any fossil site in the world. And generally speaking, what we have is, let's say we have 5 species occurring there, and when we have maximum diversity, all 5 of our species the relative abundances are all equal. And then as we kind of grade away from maximum diversity to minimum diversity, here in our sample, we have domination of that sample by a single species, in this case, this red crab here. So this would be our minimum diversity. And then we have this kind of a grade from, a maximum where it's all evenly distributed, a little bit less, and then over here towards minimum diversity. So that's diversity, but compositional variability measures the variability across many samples all at the same time. So let's have a look over here. So here are 5 samples, and these again could be anything. So this could be 5 time steps, 5 latitudinal bins, whatever you're using to assess the relative abundances of an assemblage. So each sample in this case is fairly diverse. So in this case, there's no difference between them. They're all fairly diverse, but we have no compositional variability. On the other side of the coin, we look over here. Each sample has no diversity. There's a single species in each one of those. But between our samples, we have maximum compositional variability because everyone is completely unique when it comes to its assemblages. So again, similar to with diversity, we can then apply a kind of grading between no compositional variability and moving over to the right to maximum compositional variability. And ideally, what we want to do is apply a metric to that and assign a value in particular to that. So we can look at the kind of differences in compositional variability between sample sites, between times, between space. And that's exactly what Micah did. So Micah developed a framework, which he called FAVA, to measure compositional variability across any system. So where we're looking at relative abundances, and in this case of any categorical variable, so it could be species, families, functional units such as eco-groups or morphogroups. So it can be applied to any kind of categorical variable when we're looking at the relative abundances. So in this case, we have our samples. So these samples each have their different assemblages, and which we're measuring variability across. And 2 key ways that we've been looking at this, but this can be in any kind of way, is to look at both time and space. So in this case, our different samples can be different time points. So here we go, moving from left to right. This could be start of the Cenozoic, the end of the Cenozoic. And in this case, we've been looking at something we call temporal FAVA, which is looking at the stability of assemblages through time. And on the other side, we're looking at space. So spatial locations, so in this case, let's say from the poles towards the equator, different samples, looking at spatial FAVA and looking at the heterogeneity of assemblages over space. So if you are interested in this kind of metric, I implore you to have a look at Micah's FAVA package on R and the paper which introduced this package. She'd be able to describe this metric in a lot better detail than I do. But if you do have any questions about how to use it, you could always email her or read the paper and look at the instructions and the README file for FAVA in particular. Okay, so now let's look at some of that temporal variability over the Cenozoic using our functional, ecological, and morphological groups. So This is work in progress that we are currently have submitted and is in review in Science. And what we have is we've looked into eco-group, morpho-group, and species through time. So these plots in particular are just interesting to show you the relative abundances of different kind of eco, morpho, and species groups. We get these massive changes in eco morpho group, which are kind of similar, but species, because as I mentioned, they're evolutionary ephemeral, they kind of, where eco groups kind of are always present, especially like you can see like certain colors are always there. Our species, you can kind of see the succession of species moving through the Cenozoic. So what we did in particular was take the entirety of the Cenozoic and compute farther in sliding windows of 5 million years. So this is Micah's animation of sliding windows. Looking at 5 billion years or years wide, kind of 5 tie points, looking at the stability through time. And what this allows us to do, these kind of 5 million year time bins, which are represented by these bars here. So throughout this section, the colors eco group corresponds to blue, morpho group to yellow, and species to red. I apologize if any colorblind viewers can't see any differences there. I think that it should be okay. But what these 5 million year windows allow us to do is kind of look at the compositional variability in each of these. If we move at 1 million year at a time, we just move that 5 million year window along as we go. So it really allows us to look at the kind of macroevolution of our group, but it doesn't allow us to look at the kind of nuances of like very high resolution events like the Paleocene Eocene thermal maximum, which is occurring on a kind of sub-million year timescale. But ideally, if you were to look at a higher resolution at certain intervals, you'd be able to apply a much finer resolution. So, but what is being shown here? So in this case, we have time on the bottom, like our previous plots, and temporal father on the y-axis. And basically what temporal father is measuring, as I mentioned, we want a metric to be able to assess kind of compositional variability, is and higher temporal father means less stability, less temporal stability within these organisms. So throughout all of these plots for this section here, higher father means less stable, more heterogeneous, etc. So the key patterns that we get, because there is some nuance here, but the key aspects that we can see is that we have this kind of U-shaped trajectory of stability over the Cenozoic. So this kind of, the Cenozoic is bookended by this period of high instability here and high instability in the last 5 to 10 million years. So we believe that the KPG mass extinction occurs, and the reason why we have such high instability within our different functional and species groups is because we're bouncing back from a mass extinction. The ecosystem is restructuring itself, and it's just kind of working towards this more stable kind of assemblages as we move basically through the most of the Paleocene is unstable until we get to the Eocene. That's when our kind of stability kind of gets refounded. The weird thing though is that as we move towards the modern, our assemblages are getting more and more unstable increasingly, and we believe that this is similar to what myself and Anshuman showed in our eco-group specialization index, where this kind of generalized organisms are migrating towards the equator. There is this heavy restructuring of assemblages as we move towards the modern, likely due to the establishment of the bipolar cryosphere. And this kind of reiterates some of the things that myself and my colleagues have been working on recently, that the way that biodiversity looks like in the marine realm in the modern appears to be the exception, not the rule, when it comes to the rest of the Cenozoic, which is really interesting and needs further investigation. The other kind of two key events which pop out are related to the Eocene-Oligocene transition, so around 34 to 30 million years ago. Our morpho groups are showing higher instability, which is something that we've noticed for a long time in just kind of looking at assemblages. They become morphologically really depauperate after the Eocene-Oligocene boundary. And then interestingly, at 19 million years ago, centered around then, where we have this kind of interval that we're investigating, part of the early Miocene working group, we also see high temporal stability, which is again something that requires further investigation. But one of the key questions is, does this pattern of temporal stability depend on latitude? So this is kind of a global measure of temporal stability, but if we were to look at all of our latitudes, is this kind of like, do we always have, when we have a period of instability, is it unstable everywhere, or is it just in certain locations around the globe, and does that change? And that is what we are showing here. So this pattern, which is we've termed as a latitudinal gradient of stability trajectories, is basically if we were to assess, if we were to assign all of these values to latitude rather than just global, this is what that would look like. And we looked at whether or not the certain areas have become more stable or more unstable as we move through the Cenozoic. So on this plot, here we have the equator, and here's south of the equator, and here's north of the equator. And anything which is on 0 means that that region has basically not changed in its kind of overarching assemblage stability through time. And anything which is below the line, it has become more stable. Anything above the line has become more unstable. So what we've noticed is that over the Cenozoic, equatorial assemblages have become more and more stable, whereas in the polar communities, they've become more and more unstable, which is probably to do with this kind of descent into the ice house as the Earth has cooled from 50 million years ago. The tropics probably went from being very hot to a bit more kind of stable, a bit more accommodating, whereas the polar regions, because of that drastic cooling, and now we have poles literally, we now have these more unstable communities as we move through those 50 million years. Okay, so we've looked at temporal stability. Now let's look quickly at spatial heterogeneity. So in this case, we're looking at space rather than time. So in all of these plots, we have equator represented by a dark, thick green line. We have plus and minus paleolatitudes away from the equator, and each of these panels represents about 5 million years. So here we have 66 to 60 million years ago, 60 to 55, moving forwards, and then here we have 5 to 0. So we're looking at the kind of spatial heterogeneity in this case. And again, higher farther means more heterogeneity in this case. So what we see here is that for the earliest part of the Cenozoic, our equatorial regions are the most spatially heterogeneous, and our poles are very, very stable. But then we get to the last 20 to 0 million years ago, and the equator is the least heterogeneous, and our poles are highly heterogeneous. So we have a complete reversal of what is going on through the Cenozoic. But we have this kind of transitional zone between those two end members. But what is really interesting actually is for the last 30 million years after the Antarctic ice sheet forms, we're having this really weird, distinct pattern of this kind of seesawing. So this kind of latitudinal seesaw of heterogeneity in the past 30 million years. So these plots here, ecogroups on the top, morphogroup on the middle, species on the bottom, are 5 million year time bins, 30 to 25, 5 to 0 here. And in this case, what we've done is split it into occurrences near the equator, occurrences in the southern hemisphere, occurrences in the northern hemisphere. And what we see is from 30 to 25 million years ago, our highest heterogeneity is in the southern hemisphere. Then it stabilizes for 10 million years. Then our highest heterogeneity is in the northern hemisphere between 15 and 10 million years ago, restabilizes, and then in the last 5 billion years, we have heterogeneity in both polar regions. So again, it looks like the last 5 million years or so in particular are like the exception and not the rule when it comes to patterns of marine biodiversity. Okay, I have a couple minutes left. I should be able to get through this section relatively quickly, but let's have a quick look at some work I've been working on for the last few years on the Eocene-Oligocene transition. So this work, looking at 34 million years ago, looking at this time with the Antarctic ice sheet first became permanent. And this study just looking at the ecogroups, looking at the species richness within each ecogroup, and then using the Triton dataset, 1 million year time bins across the entire greenhouse icehouse transition from 56 to 25 million years ago, and looking at paleolatitudinal bands of about 5 degrees. So let's just quickly go through the 4 kind of key eco groups, the 1 to 4, and see what they're doing throughout this time. So these warm water surface mixed layer dwellers with symbionts, they start out with very high diversity in the Eocene, and as we move towards the Oligocene, we get our lowest diversity at the boundary, and then some recovery in the early Oligocene. But we get these kind of 3 richness peaks within our eco group 1. So bear that in mind. If we then move across to our asymbiotic forms in the surface mixed layer, they show a kind of similar pattern. Their highest diversity is in the interval just before the Eocene-Oligocene transition, and then they get hit relatively hard, a reduction in richness. But again, in the early Oligocene, we have these kind of vague little biodiversity peaks which persist into the Oligocene. I will show you a plot where it's a little bit clearer. I'm not just hallucinating. Then we move a bit further down in the water column to these thermocline dwellers who like it a little bit colder. They did not like the warm house world of the Eocene, but as the Earth has cooled, their richness has slowly increased, and they really liked it in the Oligocene. And again, kind of minor peaks in biodiversity in the Oligocene, especially in the early, after a couple million years here. And then finally, our coldest, deepest dwellers in the subthermocline, very similar pattern to our thermocline dwellers. They really like it when it's cold, probably because they're in the deepest, coldest part of the water. And again, they show high richness in the low latitudes. So why are we getting these 3 distinct peaks in our richness amongst our eco groups, and what is happening? If we look at the modern latitudinal biodiversity gradient in the marine realm, we see that it is actually bimodal. So unlike the terrestrial realm, where it's pretty much smack bang on the equator, we have these bimodal peaks within the mid-latitudes. Here is the LBG from planktic forams in the modern by Marinarillo et al. And these bimodal peaks is mainly due to differences in temperature structure of the ocean, and also oligotrophic gyres within the mid-latitudes. If we look at the late Eocene, so work led by Isabel Fenton back in 2016, here we have our late Eocene latitudinal biodiversity gradient. So here's the equator, here's 60 degrees. Our modern one is this dashed line, similar pattern to what Marinarillo showed. And it's this kind of bimodal one, similar to the modern, but just muted compared to the modern. And if we look at our Triton data and the work that we're looking at, 37 million years ago, we see a similar pattern, especially in the Northern Hemisphere. We have a dip at the equator and kind of slight peaks within the mid-latitudes. If we look at the early Oligocene, though, I told you I wasn't hallucinating. We have 3 distinct latitudinal biodiversity gradient peaks in all of our eco groups. If we combine them all together, it does still exist. They're not cancelling each other out. So what we think is potentially happening here is where we have these mid-latitudinal peaks, which are the same as what we have in the modern, are probably driven by a biological pump, an early establishment of the biological pump across the EOC, or increased efficiency of the pump anyway. But the low latitude peak, which is not present in the modern, is probably a relict thermal niche from survivors from the Eocene into the Oligocene, where they evolved in a greenhouse, so they want to stay where it's still warm. And we think this is possibly analogous, as I mentioned before, to the mid-Miocene cooling patterns, where Flavia Boscolo-Galazzo and colleagues looked at the last 15 million years and showed that this cooling would have slowed down the breakdown of organic matter in the water column, allowing more food and more oxygen to get deeper into the water column, which would ultimately lead to our patterns we see in our latitudinal biodiversity gradient and the patterns we saw in our eco group specialization index. So I've got about 20 seconds left technically, but just really quick wraparound conclusions. Micah's work showed that the Cenozoic is bookended by these periods of great instability in the early and late part of the Cenozoic. Over the Cenozoic, equatorial assemblages appear to be stabilizing while polar communities are destabilizing. We have this latitudinal seesaw in spatial heterogeneity over the last 30 million years. And then potentially we have this kind of proto-oceanic twilight zone being established across the EOT, with some of these kind of relict Eocene survivors hanging on at the equator. Thank you all for listening, and I'm happy to take any questions.
Thank you very much for a great talk, Adam. That was super interesting, and I think the audience agrees if I look at all the clapping emojis. Yeah, just a reminder to the audience, you can either send your questions directly into the chat, or you can send them to someone, questions@paleoperks, if you want to stay anonymous. So we have received a few questions already, so I'm just going to drop those in the chat. So the first one asks, is there any particular reason for choosing the 5 million year window with temporal fava? Have you tried it with wider or narrower windows, especially since fava seems high in the last 5 to 10 million years, which is very close to the window size?
Yes, so this was one of the key comments from reviewers from our first round of reviews for the paper was that exact question. So Micah did do an amazing job and looked at multiple different lengths of sliding windows, not just number of sliding windows, but also the resolution, dropping it down to 500,000 years or so. And every time we looked at the patterns, did the key patterns anyway. This is why at first I was kind of really getting into the weeds of when these sort of things are occurring, but you have to really take into account like the general, if these patterns are sustained when we change the bin length and the bins and the number of bins, then we can actually say that there is a genuine pattern here. So yeah, those patterns are retained when we change those parameters.
Okay, great answer. That's good to know. And we have another question from Babel in the chat saying, thank you for this great talk. When using fava, how does that interact with species richness? Spoda species today are much less numerous. How can we infer heterogeneity from few species?
Really good question. This is one of those questions that I would direct towards Micah if she was here. But I can't really answer it in a great way. I know that Micah, again, these comments came up on the paper, and Micah had to write quite long replies within and reiterating the methods that, irrespective of the number of species, this is kind of still mathematically trying to discuss mathematics from a non-mathematician. It's still mathematically sound, irrespective of the number of species, and this is why fava actually, in particular, she mentioned is a lot is very useful compared to a lot of other beta diversity metrics because it can really account for the number of species present.
Would you like to add something, Barbara? I can unmute you if you want. No, okay, that answers the question. And I think just everyone should just read the paper once it's been published, or is it published already?
If you go on Micah's Google Scholar,
the
fava paper's on there, and this paper, hopefully, if these next reviews go well, should be out in the next few months.
Okay, great. I look forward to that. We have another question. Let me add it to the chat. Also saying, I fear this is also maybe something that relates to statistics. So if you can't answer, no problem. But the question says, great talk. How much data do you need to carry out this type of analysis? Specifically, would you be able to do a similar analysis for the global cooling of the late Paleozoic ice age, where the microfossil resolution is obviously much poorer?
Yeah, I mean, anything which has categorical variables and relative abundances, if that's species, genus, family level, anything, you would be able to apply the fava metric to.
Okay, that's great to know. And then there is another question, maybe slightly less related. Are there any concrete plans to fill in the polar gaps in Triton that you know of?
Yes. Myself and my colleagues are, because Triton is based on scientific ocean drilling records, so it's really difficult to drill in the polar regions because there's lots and lots of till, so you can't really get through it to get to those kind of earlier records. So luckily, some stuff is on land, so we are currently actively collecting data, performing a literature review to collect as much of this terrestrial data as possible, because not only will that help fill in the polar regions, but you saw those huge gaps in the low latitudes as well. That's due to a number of different things. It's difficult to drill when you get that deep in the Paleocene, but also you've got all these cherts radiolarian cherts in the earliest part of the Cenozoic record, which are horrible to drill through, and basically the cherts fracture and remove, and you lose all of your calcareous fossils like our forams. So, but there are Tethyan regions, and there are areas in places like India where there are terrestrial records, which can hopefully start to fill in some of these key gaps, because we need to know what the low latitudes are doing during the hothouse, because it's quite a warm day today, at least in the UK. So understanding what biodiversity does when it gets really warm really quickly is kind of key.
Right. That's good to know that there's work being done there. I have a slightly related follow-up question. I guess another group that has a lot of data available already are calcareous nanofossils. Are there any plans to do the same analysis on those to see if they follow similar patterns, or?
I would. It is on my to-do list. I would love to look at, because we have diatoms, not so good a record, but if we have forams and radiolarians, which are kind of zooplankton, one is siliceous, one is calcareous, and then diatoms and our nanos, one is there are autotrophs, so we can actually look at siliceous and calcareous, autotrophs and heterotrophs, and see if we get kind of similar, kind of mutualistic or kind of different patterns depending on what your biomineralization pathway is, and whether or not you're a heterotroph or an autotroph. So that'd be a really cool question to investigate in the future.
Right, cool. Thank you. And then I have one more question related to that, if you don't mind. Considering really rapid warming, the hyperthermals, I mean, I'm not a forum expert, but they don't really seem to affect them that much, or at least they were not in your summarization of major events. Is this just because they are too short-lived, or are they what is your idea about this?
Yeah, hypothermals are weird. Like the Paleocene Eocene thermal maximum doesn't really cause any extinction in our planktic forams. We get a lot of turnover, so actually they seem to just speciate when it gets hot. The key thing that really causes extinction in our planktic forams in particular is changes in the structure of the ocean. So the Eocene Oligocene transition, ice sheet forms, we get vertical, because they're using vertical migration to do a lot of their reproduction and their kind of general life cycles. A few people believe, I believe, that these disruptions in the kind of vertical structure of the ocean are these kind of triggers for extinction within the forams. And again, the relevance of that is if we suddenly melt ice sheets in the modern, we inject a bunch of fresh water into the ocean, we potentially disrupt the vertical structure of the ocean, and then can potentially, it's not actually the warming that might be the trigger for the extinction for a lot of species. It's actually the vertical physical structure of the ocean changing. That might be one of the triggers instead.
Okay, right. Thank you. I see that we have another question from Hamza in the chat asking, can this analysis be applied around earlier extinction events, for example, the Big Five, to zero in on the causes of extinction?
Definitely, yeah. I only have ever worked on the Cenozoic, unfortunately, at the moment. But like any extinction event, any time interval, again, if you have any kind of categorical variable, if that's some kind of functional group, genera, species, and relative abundances, you can apply this father metric on any area. It doesn't have to be global. It can just be a certain region. It can be a certain, if you've got a Lagerstadt, you could do it there. Any kind of biogeographic temporal region you'd like to do, it's applicable and across any event you'd like to.
Thank you very much. Very clear answer. That was it for the questions for now. I gave everyone, Hamza says thank you. So it was a great explanation. I give the audience a few more seconds to type in any final questions they may have. Otherwise, we already had 10 minutes of Q&A. So thank you again very much, Adam, for your great talk.
Thank you.
Also from Berbel, I see in the chat. So yeah, if there is no more questions, then I will just like to briefly share some information about the next talk that we will have at PaleoPerks. So again, thank you everyone for being here. Thank you, Adam, for giving a talk. Thank you, audience, for your interest and for asking great questions. Also, thank you from a lot of people in the chat I see now. So next week, we won't have a talk, but the week after that, August 18th at, again, UTC 15 o'clock, we have a talk by Katie Jemison from the University of Victoria in Canada, who will talk about paleoceanography. So tune in if you're interested. And again, a reminder to fill out the weekly feedback form, just so we have a bit of information on who attended. So yeah, I hope you enjoyed the talk. If you would like to chat a bit more with Adam about his work or about his future projects, feel free to stay for tea time. So tea time is just a relaxed chat for a few minutes afterwards. So we will turn off all the recordings and you can just turn on your camera and your microphone and have a chat. So if you want to stay for that, then we'll please first have a short break of 2 minutes, just so to give Adam a bit of a breathing pause. So we'll turn off our cameras and be back in 2 minutes, and we hope to see some of you as well. If we don't see you, then I hope to see you next time, and have a great rest of your week.